Okay, welcome back. Today we will start talking about functions. So, the most familiar examples of functions are what we would call functions from the set of real numbers to the set of real numbers, and the most familiar pictorial representation of course is as a graph. So, this is how we mostly think of functions, and what this really means of course is for each value of x, there is the function value f of x is what is denoted along the y axis. So, the point here is just x comma f of x, and we just join all these points x comma f of x as x takes all possible real values. So, recall that the formal definition of a function requires two sets, there is a domain and a codomain. So, in this example both domain and codomain are just the set of real numbers, and what we really want to say is well, here are the various points of the domain, and the function is thought of as mapping each point of the domain to some point of the codomain. So, now of course a natural question we might ask is, well, what does the function do to subsets of the domain? So, for instance you pick out some chosen subset of the domain and ask what do all the points in this subset map to under the function. So, you just collect together the images of points which come from the chosen subset and put them together and ask what set is this. Okay, so, this is often a very natural and instructive way of looking at functions. Beyond just what it does to points, you also sort of want to think of it in terms of what it does to regions or what it does to various subsets of the domain. So, let us try and do this for the familiar function from the real numbers to the real numbers. So, the question here we will ask is, what does a function typically do to a set of the following form, to an interval? Okay. So, what does this mean? What I want to do is the following: I want to take an interval, closed interval a b. This just means the set of all real numbers which lie between a and b, including the two endpoints both a and b. Okay, so, here we do include a and b, and now the question is, what are the images of the points in this interval under the function. So, now we will think of a function as being a map from the real numbers to the real numbers and ask, well, collect together what it does to the various points in this interval and ask what sort of set does one get on the right hand side. Okay. So, if we call this interval as I, so the question here really is the following: what is the image of I under f? Okay, so let us try and answer this more or less from the graph of the function. So, what we will do is, so imagine there is some graph function f and we just pick some interval, pretty much any interval will do. So, let us take for instance the interval between a and b, this is a and that is b. So, what values does the function take when x ranges between a and b? So, we will just write down all the y values. So, pictorially the lengths of these vertical lines indicate the values of f as x varies between a and b. So, we ask, well, what are the various values that the function takes? So, here is what it seems to be from this graph. There seems to be a maximum value. So, there is this largest vertical line. So, this maximum value, let us call this maximum y value as m. There is a minimum y value, let us call it small m, and observe that between capital N, m and small m, any choice of y value is always taken by f. So, you pick any y value between capital M and small m, let us say this number, let us call it y, or maybe we will call it c, and we ask, does the function take the value c? And we notice yes it does. So, here is a choice of x at which it takes the value c, and in fact there is another choice of x, let us see. So, here could be a choice of x, but this value of x here does not lie within this interval. So, we do not worry about this one. Okay. So, there seems to be just a single value of x, it is this guy here, let us call it x naught, at which the function takes the value c. Okay. So, in general there could be more than one value of x. But the key point here is the following: observe that from this graph at least it seems that if I take the function f and I take the image of the interval I, so here's how one writes this. So you take the interval between a and b, and when we write f of the interval ab, this just means the image of the interval under the map f. So in this example at least it seems to be the following: it's all values between small m and capital M. Okay, so at least in this example this seems to be true. So you just figure out the maximum, you figure out what the minimum is, and every value between them is taken by f. Okay, and that's exactly the image of this interval. Now what's the key property of the function f which makes this true? So why is this really true? So here's an example of a function for which this may not be true. Okay, for the graph that I drew it happens to be correct. Now let's do the following. Let's take another example. Let's write out the formula for the function f of x equals, well, it's defined in two pieces. It's the value x if x is positive, and it's the value x minus 1 if x is negative. So it's a piecewise defined function, and if you draw the graph of this function, here's what one finds. It's just the graph of the line y equals x. So this is the graph of the function when x is positive, and when x is negative it's more or less the same line, just shifted down by 1. Okay, so here's the graph, and the key point to observe is that this point here where the bottom line meets the y axis is not on the graph. So we often denote it by a circle like that, and this is sometimes shaded in to indicate that this point is on the graph. Okay, so what we now have here is the graph of this function f, and now we could ask the same question. If I take an interval, so let's say take the interval between -1 and +1, so just consider this closed interval here and ask, well, what are all the y values, what are all the values of the function when x ranges over this interval? So we do the same thing, we draw all the, so here are the various y values that you get, and when x sort of ranges in the positive side, at x equal to 0 you get this point here, and then you get these vertical lines. So these are the various y values that you obtain. And now again observe that the maximum value is a 1, the minimum value is in fact a -2, right. So those are the maximum and minimum values, but here's a key difference as compared to the previous case. The values of y between 0 and -1, so these y values, so you take any y value between 0 and -1, those y values are never attained by this function in this interval. Okay, so for instance if I take y equals -12 and ask, well, what value of x would possibly give me a value of -12, so I just draw this horizontal line and ask, does this horizontal line meet the graph of this function at all? Okay, and I find that of course it doesn't, right. So here is a function for which so if I take the interval I in this case to be the interval between -1 and 1 and ask what's the image of f, what's the image of I under f, the answer seems to be the following. I get, well, of course the y values here are everything between 0 and 1 certainly occurs, so it is the set of all x. So here's one way of writing this, it's all values of x between 0 and 1, those are certainly there, and if you look for what happens when x is negative, you get all values between -2 and -1. So we say that this is this set, this interval union all values between -2 and -1, but notice -1 is written as an open interval, so the value -1 itself is not attained. Okay, so here's the image of this interval under this function f. Okay, so this turns out not to be an interval, this is sort of a union of two different pieces. In the earlier example, the image of an interval just turned out to be an interval itself. Okay, it was just the interval of all numbers between the minimum and the maximum. So in other words, there are no breaks in between, so somehow that's the key intuition to keep in mind. So why was this property true for the first function and false for the second one? The key thing which made it work is what's called continuity. the fact that the graph of the function did not have any breaks. Okay. So informally, continuity just means that when you draw the graph of the function f, so like the very first graph we drew, something like this, the graph was just drawn continuously, there is no break in the graph itself. So this is an example of a continuous function, as opposed to the second graph which look like this, and this is an example of a discontinuous function. And in fact, we often say that the discontinuity is at the value of x equals 0, that is sort of where the break occurs. Here there are no breaks at any value of x. Okay. So the key property of continuous functions, so continuous functions are sort of very important, they have a lot of very nice properties, and one of them we have just seen, which is that if I take an interval of values of x, the image of that interval under this function f will again be an interval which will be all y values lying between the minimum and the maximum. Okay. So here is in fact the statement that we have for a continuous function. So let us write this out again. So here are key properties of a continuous function. So let f be a continuous function, so let f from R to R be continuous, and let I be a closed interval, let I be a closed interval. So let us say it is all now. There are two important properties. Number one, that f attains Okay. The first property, which somehow looks rather obvious, but there are examples, easy examples where we can see it may fail. So the first thing says, in fact there is a value of x at which f attains its maximum, and a value of x at which f attains its minimum value on I. Okay. So we do have a maximum value and a minimum value, let us call these m and small m. So that is fact number one. And fact number two is the thing that we just said, that it attains every value in between. So let us also say f attains every value between m and n. On the interval I. Okay. So there is a maximum value which it attains, there is a minimum value which it attains, and in fact it attains every single possible value between small m and capital M. And both these statements are very easily false in examples of discontinuous functions. So we have already seen an example where the maximum and minimum value are attained. So here is the function m, small m and capital M were both attained when you take the interval to be the interval between -1 and 1, but values between, every value between the minimum and maximum was not attained. There were values, for instance, between 0 and -1 which were not attained by the function. Okay. So that is an example where f is discontinuous and the second property fails. Now let us also look at an example where the maximum and minimum are in fact not attained. Okay. So in other words, there really is no maximum or minimum. So here is one of the standard examples. So we could take the interval between 0 and 1, but let us define the function first. So let us take the function f of x to be just the function 1 over x, but of course in order for this to make sense I cannot allow x to be 0, and so at x equal to 0 I redefine it as 0. Okay, so here again is a piecewise defined function. If x is positive, what you get is the graph of 1 over x, which looks like that. If x is negative, again it's this graph, so the same thing, 1 over x, and 0 alone is something like that. Okay. Now let us do the following. So at 0 the value is 0. So again let us try and take an interval. So let us take an interval, let us say between -1 and 1. So I will just take the same thing as before. So let us look at the interval between -1 and 1, and now we ask what are the values of f in this interval, and we observe the following. If you look at the y values, then they keep getting larger and larger and larger, right. So they go off to infinity is how we often say this. Similarly the y values for negative values of x go down to -infinity. So now if you ask, well, what is the maximum value of f on this interval between -1 and 1, so at 0 itself it is a 0, so there is no problem really at 0, but if you ask what is the maximum value, well, we observe there really is no maximum. In some sense it's like infinity. The value of f is larger than any number you can write down. Similarly there is no minimum because the value of f becomes more and more negative. It sort of tends towards -infinity, and so, well, there really is no maximum or minimum in this example. Okay. So and notice again that this is an example of a discontinuous graph because clearly there is a break at 0. So we draw the graph really is in 3 pieces. There is the negative 1 by x piece, the positive 1 by x piece, and the piece at 0. Okay. So this again is an example of a discontinuous graph, and one in which there is neither a maximum nor a minimum on the interval between 0 and 1. Okay. So having a nice continuous function will give you both these properties, that you will actually get a nice finite maximum value, a minimum value, and every value in between will always be attained. Okay. Now this second property here, that every value in between is attained, is sort of like the intuitive notion of continuity. It's a formulation of something very intuitive about continuity, that when you draw a graph in a continuous fashion, you really must pass through all intermediate values, right. So here's another way of stating this. So if I have the interval between a and b, so there's a way of stating the same thing without bringing in the maximum and minimum values. So here's the statement. Suppose I have a graph of a continuous function and I want to see what it looks like between a and b, for instance. So at a I have some value, so let's say this is the value f of a. So that's the y value at a, and at b I have again some y value. So maybe just to make it a little clearer, let's just think of both values as being positive. So I have, let's say, f of a, that's the y value at a, f of b is the y value at b. And so here's the intuitive notion of continuity. You try and draw the graph between the point a comma f of a and the point b comma f of b. Now when you do this, you pretty much have to pass through every intervening y value between f of a and f of b. So these are the two boundary y values, and it's sort of clear intuitively that no matter how you draw the graph, you're going to have to pass through every value of y in between these two boundary values. Okay. So this is sort of another reformulation of the property that we just said, that f in fact attains every value between f of a and f of b on this interval ab. So this formulation is sometimes called the intermediate value property or the intermediate value theorem. So let me just formulate this. So it's called the intermediate value theorem. It says that let f be a continuous function us say from the real numbers to the real numbers, you in some sense you really only need it on the interval AB, but for now let us not worry too much about this. So let f be a continuous function from the real numbers to the real numbers, and let us just restrict attention, let us call I to be the interval AB. Then given any value between A and B, given any number C, any real number C, where does C lie? It is a number between A and B. What can one do? So let us take a number C between C is between f of A and f of B. I should have been careful. Given a real number C between f of A and f of B, so it is a y value between the two boundary y values. What I can conclude is there surely exists a point on the graph, so let us call it x0. There is an x value at which the function takes the value C. So given any number C between fa and fb, there exists an x value, let us call it a real number x0 between A and B, such that f at x0 is exactly the value C. Okay, so this theorem here is called the intermediate value theorem. The proof uses some very important properties of real numbers and so on, so we won't get into the formal proof itself, but this much should be clear that it is a rather intuitive property of continuous functions, somehow capturing the feeling that you sort of don't really lift your pen off the paper when you draw the graph from the two endpoints, well, going from one endpoint to the other. Okay, and this somewhat simple looking property has lots of very interesting applications, and we will look at least a few of these applications next time.